a little delay here. First of all, I'd like to thank the organisers for the opportunity to talk about my research. It's a recent work we have on SME6. And today, I'm going to be talking through some QPI measurements of the surface states. And I want to highlight why we think this is an important and exciting result. So this work is done with samples from the Physics group, and we've had some useful conversations with theorists along the way. I'm going to start with a little bit of an introduction to topology. This has been something that's been mentioned so far. I'm going to go a little bit more into it. And I want to motivate that by thinking about how we classify different phases of matter. So traditionally, we're looking for a spontaneously broken symmetry. In going from a liquid to a solid, there's an average translational invariance that is broken. Similarly, you can create a ferromagnet by breaking a spin rotation degree. But if you try and tune between a band insulator and a quantum Hall or quantum spin Hall state, then there is no spontaneously broken symmetry. You can create a quantum Hall state by applying an out-of-plane magnetic field. You quantize the electron's motions into Landau orbits, and if you tune the field just right, you can create an insulating ground state just like a band insulator. But these two states are very different. In particular, if you measure the Hall voltage, in this system you find that it's quantized in units of E squared over h. So these two systems are examples of different topological order, and this filling factor nu is an example of a topological variant. So what do I mean by topological order? I will call two things topologically equivalent if I can tune between them adiabatically. That is, keeping the system in its ground state. So here's an example. If I have a Hamiltonian that depends continuously on some set of parameters r, that could be a hopping amplitude or an interaction strength, then the values R1, the system might look like this and be gapped around the chemical potential. And at values R2, the system is also gapped, but a little bit different. Then these two systems are equivalent if I can tune continuously between them. And what I want you to give you a sense for is that it's harder to keep the system in its ground state as the band gap gets smaller. So here I've represented that when I make the band gap smaller, it's harder to avoid excitations, so it's taking me a longer time to tune between two consecutive R values. So another way of saying that is the time it takes to tune between consecutive R values is inversely proportional to the size of the band. So what is topological inequivalence? So quite naturally, that's when this connection does not exist. You can think about it as the band gap gets smaller and smaller, it gets harder to make any changes adiabatically, and for some parameter values, you simply don't have a connection. And it's quite natural here that the band gap must go to zero. So to reiterate, the distinction between topological phases of matter necessitates a conducting boundary. And we see that in a quantum Hall state. Semi-classically, think about these Landau orbits skipping off the boundary. You have a positive moving state on this side and a negative moving state on the other side. Okay. To create a topological insulator, you need to preserve time reversal symmetry, and you can do that by stacking two copies of the integer quantum Hall event. And they have a cancelling charge current on the edges, but a non-zero spin current. Something I want to mention here is that these boundary currents are protected by a topology. I can shift this boundary arbitrarily, but I still need to have the band gap. So far, everything I've been talking about comes from a non-interacting theory. You solve a single particle Hamiltonian to find your block states, and then you fill them up with fermions. So your excitations are also fermions. But if we move to an interacting system, then we can remove this requirement. So in general, we can have an anion excitation where we pick up an arbitrary phase under exchange. So here I'm showing an example where I do a double exchange on two particles. In the case of a boson or a fermion, this is a trivial state, but in an anion, I can pick up an overall phase factor that I can use to encode quantum information. If you do this with three or more particles, then you formally get a braid group where your operations are two particle exchanges, and that group is non-abelian. And systems like this, where you have topologically protected quantum information, are very exciting for applications in quantum computation. So we think that SMB6 is a promising candidate for hosting these types of excitations. It's been known for a long time that a bulk gap forms on cooling due to strong electron interactions, and that at the lowest temperatures, this flattens to a plateau which is dominated by surface conductance. additionally, there's been some early theoretical proposals of a topological state in the system. So this is quite an exciting material we think to study. There's already been some great introductions on SMB6, so I'll fly through this pretty quickly. You have localized 4x states, that's a flat banding K-space, and itinerant 5D states that look parabolic. If you zoom in close to the chemical potential, then the 4f states are split by crystal field interactions, and the 5D state is almost parabolic. If I want to connect this to the transport measurements, then I focus on the states that are close to the chemical potential. So at high temperatures, where this is a metal, these states don't interact. But as I cool down, you see a band gap opens initially below the chemical potential. In this scenario, there will be not a strong effect on the transport. As the upper hybridized band lifts above the chemical potential, you have a sharp upturn in resistivity, and if you take a surface projection of your bands at low temperature, you necessitate this band gap to be crossed by surface states. So in addition to the transport measurements I talked about, a number of other probes have been looking at surface states on this material, in particular ARPAs, where there's some indication of spin texture. But so far, a Dirac-like dispersion, in particular crossing of surface states, has not been identified. We're also interested in looking at the effect of having multiple hybridization events close to one another, and what that can have on parity inversion of the system. In general, these systems are difficult to probe because of the very small energy scales. And so this motivates a study using STM, where we can get simultaneous energy and momentum result imaging with a high resolution. Okay, so let me talk you through our experiment a little bit. This is a picture of a single crystal that we studied. It's grown with the aluminum flux method, and it's cleaved in cryogenic UHD. It's then inserted directly into our STM. When we scan on the surface, we find a lot of disordered regions. But we do find some ordered regions. This has been talked about a little bit, the 2x1 reconstruction. It forms a non-polar surface. That's the one we're going to study. You can operate STM in two modes. You can study topography like this, where you can park the tip at a location, sweep the bias, and measure the differential conductance that is proportional to the density of states. If you take a measurement here, you might take a measurement here. If you take a measurement at every point in this image, you build up a three-dimensional data set. So here, at each image is the density of states that is resolved spatially, and you have that as a function of energy. Okay, there's a lot of information contained within this, and we're going to try and disentangle parts of it by thinking about quasi-particle interference. If you have an initial state that scatters off an impurity, goes to a final state KF, then you get an interference pattern that's characterized by a wave vector that is the difference in momentum between the initial and final states. For example, in simple metal, your initial and final states are constrained by your bands. They must lie in a circle like this. You can have scattering here, which will correspond to a pointing Q space. And if you trace out the scattering vectors you can have, you get a circle in Q space that is twice as big as that in K space. So what does it look like in real space? You have defects that emanate an interference pattern with a wavelength that's 2 pi over Q naught. So if you haven't looked at these things before, this little simulation will help you a lot. Over here I've got a K-space band structure for a simple metal, it's just parabolic. Here I've got the Q-space Fourier transform, which should look like cuts in the band structure of particular energy, but with twice the size. And here is real space. I have a bunch of defects in the simulation, and you can see a standing wave pattern graph. And I'm going to play a movie that sweeps through the energy. So you see this pattern dispersing nicely. This ring grows as you move up the band structure. So for our data, we do the same thing. We take a Fourier transform and we analyze these images for dispersing patterns. So I'm going to play you two movies now. This is data taken on SMB6 on a 2x1 reconstruction. First, I want to look at the real space DIDV. So this is measurement of the density of states. And to try and see dispersing patterns here, focus on a defect, maybe this one up here. Okay. So I'm playing this through. And you can sort of see something is changing around the defect. Quite a lot at the end. But I think it's hard to see. So now let's look in Q space. This peak here corresponds to the surface reconstruction. And this is the center, and our signal is concentrated in this direction. So what you should see as I speak this is something that starts here, moves in, and then moves out. Okay. So it starts there, moves in, and then moves out. pretty tricky to see. There's some stuff going on at the end that I'll talk about later. So what I'm going to do to try and make this more obvious is by taking an arc average here. If I plot out different energies from that section, the data is shown in blue here. There are three main contributions that I'm concerned about. We have some disorder at low Q. We have a surface reconstruction that is non-dispersive. It's always at the same Q value. And there is one further signal that disperses quite rapidly as we change the energy. This is what we attribute to electronic Q value. If I have these three signals and only one is interesting, I can subtract out the two that aren't, and I'm left with something that is just the electronic solution. So let me do this for every single energy and build up a plot that looks like this. So now this is formation of heavy bands. This data is taken at 8 Kelvin SMB6. You see heavy bands here and hybridization here. I've blocked out this region here so that I can compare to calculations of the bulk bands. So I don't want to look at the surface states yet, I'll come back to them. And you see something going on here as well. If I take the peaks here and I plot them on this band structure, they look like this. You have to interpret this scattering as being in the next group to get this image. But it lines up quite nicely. We've taken similar data sets on 3 different areas, and there's a very good agreement between them all. So we think that a picture like this describes the bulk bands quite accurately. We have one other measurement we can do to check this. It's the DIDV. I'm plotting this a little strange. So this is increasing density of states. So this is a peak here in the density of states, and this is another peak. And you see they line up very well with where the bands flatten out. Now we're going to focus on this measurement of DIDV, which I can take quite easily at different temperatures. And I'm going to construct a model that based on QPI data, but here I'm using just a 2-band model. I'm just using this band as this band. I'm ignoring a lower hybridization. And from the model, I want to extract 2 parameters as a function of temperature. I want to get the size of the direct hybridization here and use that as an indication of when the hybridization turns on in this material. And I want to extract the energy and momentum position of the indirect gap to make comparisons to the transport measurements and to see where the surface state should lie. Okay. So here's the result. The data here is the white circles and fits of these solid lines. They don't fit well in this region, and that's where the second hybridization event is. And there's a few things I want you to notice. This is the parameters extracted. Okay, so on this axis, this line here corresponds to the size of the direct gap. What we find is that it's non-zero for all the temperatures we measure. We have hybridization, and we measure up to 50 Kelvin. If I extrapolate, I think this is non-zero up to 150 Kelvin. More importantly, we find the indirect gap here is it's between these 2 points, and it starts out below the chemical potential and grows at some point. It crosses the chemical potential. The crossover temperature is 33 Kelvin, and that lines up nicely with the upturn in resistivity. But most importantly of all, we've worked out the gap for all of the temperatures, and in particular for the lowest temperature. So now we know where the hybridization gap is at the low temperatures from our model, and we can go into those temperatures to look for surface states. Okay, so what I'm showing here is our lowest temperature, DIDV measurements. This is the region that I identified as a hybridization gap, and what you can see is there's a slight kink as it enters that region. If I try and fit this data with a model that describes the bulk physics, it's quite a good fit, except for within this gap. If I look at the difference, I have a pronounced peak in that region. My logic is that if the model describes the bulk physics, then a discrepancy is a surface state. So we think we have surface states within the bulk hybridization. The final piece of evidence is in the QPI. So let's re-examine the QPI now within this region at a higher energy resolution and see if we can see something. So here is that data. To remind you, this peak here is the Bragg peak that's coming from the surface reconstruction. This is the center of the scan, and again, the signal is concentrated in this region. So these energies now are much, much smaller. They're all within the gap. So as I step through this, you see a signal that clearly disperses towards the center. So let me run through that again, there it goes out, and here it comes in towards the center. Okay, and if I do a background subtraction, then I can get an image that looks like this. So this is a clear crossing of a state that exists within the bulk hybridization. So I just want to finish by putting this all together into one consistent picture. First, we use QPI imaging to directly measure the bulk bands. From that, we construct a model that we use to fit the DIDV temperature dependence. That tells us where the bulk hybridization gap is, and if we try and fit in that gap, we find a discrepancy indicating some surface states. Then when we re-examine the QPI within that gap, we find this dispersive surface state that bridges the hybridization gap. So from here we have some interesting thoughts about where we'd like to go with this. In particular, we're concerned about trying to find anisotropy in the hybridization and see if we can use it to extract information about the topological. And with that, I'd like to thank you for your attention.
The energy width of your surface band and your interpretation, is that limited by your experiment, or is that intrinsic to the surface quasi-particle?
The energy width of this?
Yeah, I see the red streaks have a finite extent vertically.
Yeah.
Is that a mean-free path?
My guess is it's mostly temperature. This is taken at 8 Kelvin, and so your broadening should be 2 MeV, something like that. So I think that's probably mostly coming from
It's not how much you're changing the voltage in the derivative or something technical.
I don't think so.
Very nice talk, thank you very much. Do you have a sense for how robust the surface states are? Have you done anything something wrong, maybe like hail that seems disappears or anything like that?
Yeah, that's a really good question. So we haven't, but we'd love to. What I can tell you is that, this is a very hard thing to image, and taking a QPI dataset to find it is also very time consuming. And what we have done is we've done DIDV measurements at high field, at 9 Tesla, but we see no change. But in those measurements, we weren't specifically looking within the gap, and we didn't know about the surface state then. So I think this is something that's really exciting to revisit. Yeah, thanks for the question.
Any particular reason why you pick up the 2x1 surface to do this QPI and not some other maybe non-conservative surface?
Yeah, that's another good point. I think we talked about this a little bit. The main reason is that it's the easiest one to find. So you have to be pretty lucky to chance upon a 1x1 reconstruction, a 1x1 termination. I'd love to take data on it, but we haven't. The other problem is that you have a polar surface, and we want a non-polar surface. So that's why we chose it.
Another question?
Sorry. Do you have the temperature dependence of your surface state? Like, how do you know what temperature how it evolves when you heat it up?
We don't, and I guess this is because we haven't got QPI data at higher temperature. If I look back at the temperature dependence of the DIDV, I don't think I can say much about the surface status.
If I may, sorry, is there any reason why the gap, your hybridization gap and the red gap opens up? Like, any reason? Is there any theoretical understanding?
You're saying why is this so linear?
Yeah.
I have no idea. I don't have a good answer for that. This is what we extract from the model. It looks kind of linear to me, so I put a little linear twinkle into it. I don't know why it should be.
Related question on the subject of temperature. How long is the cleaved surface, how long is the experiment? How long is the cleaved surface used?
That's a good question. So the experiment, the QPI experiment, will take several days.
And is
So
it ever
different
brought to room
days.
temperature?
If it was brought to room temperature, it would be weekly. We haven't looked at the same surface after cycling to room temperature.
Do you see significant differences over, because like Zach Biss's recent paper and what I showed yesterday, it seems like the surface does change significantly over a day of time, or over certainly with temperature. If you maintain it at very low temperature, bit slower. But
Yeah, and I don't think that would surprise me. What we see is a lot of disordered regions on the surface. And I think that if that's changing as a function of time, I mean, this is a polar cleave. So I don't think that would surprise me.
there are differing interpretations of that, but we can talk.
Okay.
Simple question. In your data, can you tell me what your total surface velocity is at that solution? Anything?
Yes, that's a good question. So here it disperses, this is 1 pi by a to there, 1 pi by a, 2 pi by a over 10 MeV. That's very fast in comparison, or very slow. So the RPEZ surface states they're almost vertical, right? You don't see any dispersion like this. But I think in some theory papers, this is what was predicted. So it compares better with theory than it does with RPEZ.
Another question?
So it's very interesting. What I was curious about, I think maybe you mentioned, but maybe I thought about is there's also been neutron work that talks about some kind of expectations. Have you thought about how this relates?
Yes. So we got quite excited when we first saw that data because the dispersion that they see is something that's quite similar to this. But my understanding was that was a spin exciton, a spin excitation. And I don't think that we would couple to that very strongly.
Okay, let's thank the speaker. We've run just a little bit late. That was the last talk of the day.